Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, I am going to show you how to verify trigonometric identities. This is the second lesson in our chapter for analytic trigonometry. Last lesson, we talked about just simplifying trigonometric identities, and when we want to verify an identity, basically all we're trying to show is that one side of an identity is equal to another side. So in this lesson, we know we're going to have identities. We know that the left side is going to be equal to the right side. So it's going to be our job to basically show that both sides are equal. And we kind of have some steps and some things to work on to be able to show that. Obviously, one of them is going to be what we did last chapter, or last section, which was just simplifying using identities, but also working into some mathematical operations, which I will kind of help you with in this lesson. So really, the fastest thing what we're going to learn is how to verify trigonometric identity. So obviously we talked about some identities are very basic, and then we're going to do a little bit more advanced problems in today's lesson. So one thing that we did not finish in the last lesson was simplifying trigonometric expressions down to a single trig function or number. And a lot of times, sometimes it's very obvious how to verify an identity, what you need to know, but sometimes you're going to have trigonometric identities that are so complicated, and then the other side is so simplified, you really need to practice that simplifying. So this is really kind of taken from last lesson. If we had more time last lesson, I would have added it into there. But I really wanted to focus on just, applying identities, applying simplifying algebraic and arithmetic operations to practice that with the students. So let's just kind of go through my thought process here on this one. So the first thing is, if I see a trigonometric expression, and again, now we're trying to simplify this, right? You can see here we have 3 trig functions. We're trying to get this down to 1 trig function or a number. So first thing we want to do is see what kind of operations can I apply. And you see that I have cosecant being multiplied times cosecant of x minus sine of x. So let's just apply distributive property, right? If it says to multiply something, let's multiply it. So cosecant times cosecant is going to be a cosecant squared of x. Cosecant of x times sine is going to be 1, right? Because cosecant times sine, those are reciprocal properties. So that's going to be minus 1. Now we just need to really remember what our trigonometric or our Pythagorean identities are. And I always get these mixed up too. So therefore, I'm going to write sine squared of x plus cosine squared of x equals 1. That one I have memorized. And if I wanted to obtain cosecant, that means I'm going to divide by sine. So if I divided everything by sine squared of x, divided by sine squared of x, divided by sine squared of x, I'd be left with 1, not equals, but I'd have another identity, which is 1 plus cotangent squared of x equals cosecant squared of x. Okay, so if I had cosecant squared of x minus 1, I just subtract the 1 over to the other side. Therefore, I can see that this is now can be written as cotangent squared of x. So there you go. Now in this next one, I can multiply these, but it's like, what is cosine times cotangent? So that's why we kind of practiced last chapter here. So what I'm going to do is, I don't really notice anything can really be applied or simplified. So what I'm going to do is I'm going to use the quotient and the reciprocal identities to rewrite each of my terms here. So cosecant, I'm going to rewrite as 1 over sine of x minus cosine of x. I'm going to leave that as is because I see that cotangent of x can be a cosine of x over sine of x. Now, the reason why this is important is because if I want to subtract these, right, this ends up now being a 1 minus cosine squared of x all over, let's write this. This ends up being, 1 over sine of x minus cosine squared of x over sine of x. So now I'm trying to subtract these two fractions, and they both have sine of x in the denominator. So therefore, I can just rewrite this as 1 minus cosine squared of x all over sine squared of x. Now again, that still is not to one single trigonometric function or number. But again, looking up here, I realize if I subtracted a cosine to the other side, right, instead of dividing by sine here, get rid of that. So if I subtracted a cosine squared of x to the other side, I would have 1 minus cosine squared of x, and that's going to equal sine squared. So therefore, I am going to be left with sine squared of x over sine of x. And again, sine squared of x divided by sine of x is just going to simplify to a sine of x. All right, in the next example here, this one I could go ahead and simplify. This one kind of makes sense. Like again, you don't really want to add these, right? But again, if I rewrite this as cosine squared of x, let's be sine over cosine. So if I wrote this as sine squared of x over cosine squared of x times cosine squared of x, now you can see that the cosines divide out. Is that what I did here? Oh, no. Yeah, so if you do that, right, but then you still have to combine cosine squared and sine squared, and it doesn't seem like that's really making anything easier in this case. So, and that's one of the key important parts is, I worked through this problem, it kind of brought me to a dead end, right? Or something where I don't see it's really going to simplify to a number or a trigonometric function. So I'm going to stop and say, what else could I do? Well, here we applied multiplication, here we combined. And what is another common operation that we have used in mathematics up to this point? And that is factoring. You can see that both of these expressions have in common a cosine squared of x. So if I factor out a cosine squared of x, I'm going to be left with a 1 plus a tangent squared of x. Now, I don't have that written up there, but if I was to obtain a tangent squared of x, that means I would be dividing by cosine. So therefore, my last identity would be tangent squared of x plus 1 equals secant squared of x. So therefore, you can see that this is going to equal a secant squared of x. And cosine squared times secant squared is going to be equal to 1. All right, then working on to the next one. Again, just kind of going back to those identities. Cosine squared of x minus 1, that one's a little bit different here because if you cosine of x minus 1, so if you're going to subtract 1, then you need to subtract a negative sine squared of x. So therefore, that'd be a negative sine squared of x all over 1 minus cosine squared. If you kind of look back at this, if you just subtract a cosine squared of x, on the other side, you would have a positive sine squared. And therefore, I have a negative sine squared of x divided by sine squared of x, and that's just going to equal a negative 1. So hopefully you're at least getting this idea because this is this practice of simplifying these expressions is going to be what we're going to be using in verifying identity. So that's, again, we haven't verified any identities yet, but this is why we're kind of working through this. This is our kind of the warm-up there. For number E, we have subtraction, and there doesn't really seem much I can really do to simplify them, but I do see that these do not have common denominators. So I know that if I need to subtract things, I can always use common denominators. So if I multiply by 1 minus sine of theta on the left side, and if I multiply by cosine of theta here on the right side, now they will have a common denominator, right, of cosine of theta times 1 minus sine of theta. So on this left-hand side, and let's make sure, remember that's a negative, right? So you can make that a plus, a negative. So you're really distributing those two. So let's go ahead and write them under the same common denominator. Here I'm going to have a cosine squared of theta minus sine of theta, right? Negative sine of theta times 1, and then negative sine of theta times negative sine of theta is going to be a positive, cosine squared of theta. Oh, sorry, sine squared of theta. Okay, and that's going to be all over cosine of theta times 1 minus sine of theta. Now, you could multiply that out, but again, our goal here is to get this down to one single trigonometric function, right? So it's important here that you recognize that cosine squared plus sine squared, again, is going to be equal to 1. So therefore, I can now simplify this to 1 minus the sine of theta all over cosine of theta times 1 minus sine of theta. Now, again, we don't want to take the ones and the negative signs, but actually we can look at this as the quantity of 1 minus sine of theta divided with 1 minus sine of theta is now going to leave us with 1 over cosine of theta, which is going to equal to secant of theta. So you can see just kind of how we worked our way up there. Was that supposed to be? Yeah, okay. You can see how we kind of worked our way with getting those just keep on applying the operations and then working to simplify. And again, this last one is, again, you see like it looks really confusing, like multiplying, these. But again, if you remember, these are the difference of two squares. So this is something that's really important. Remember, a minus b times a plus b is equal to a squared minus b squared. So in this case, you recognize that these binomials have the same terms, just one's positive, one's negative. So in this numerator, I'm going to see secant squared of x minus 1. And the denominator, I'm going to have 1 minus cosine squared of alpha. And what's really nice about trigonometric functions, when we are using the difference of two squares, they're going to produce these Pythagorean identities. So what we need to look at is what? What is secant squared of x minus 1? So I go, okay, so secant squared of x minus 1. If I subtract 1, then I have secant squared of x minus 1. So that's just going to be equal to tangent squared. And then 1 minus cosine squared of alpha, again, if you just subtract the cosine squared of alpha here to the other side, that's going to equal to sine squared. All right, but again, we do not have this written here, or we do not have this simplified down to one trigonometric function. So therefore, what I'll do is I'll just rewrite this as, instead of dividing by sine, I could also multiply by cosecant squared of x. Now what I'll do is I'll just rewrite using the quotient and the reciprocal identity to see what is going to divide out. So this can be written as sine squared of x over cosine squared. Did I change my angles? I did. Was that an angle? Oh, that's alpha and alpha. Jeez, oh man. I think this got messed up. So here, that's kind of a hack. Just fix all those x's to be alphas. Okay, and then cosecant squared of alpha is going to be 1 over sine squared of alpha. And now you can see that, again, the sine squareds are going to divide out, which is going to leave me with a 1 over a cosine squared of alpha. Well, again, if 1 over cosine of alpha, or 1 over cosine of theta is secant of theta, then 1 over cosine squared of alpha is just going to be secant squared of alpha. Okay, so that's the simplifying part. And when I get to these verifying identities, you can see that's exactly what we're really going to be doing in this chapter. This is a really good practice for the students. So basically what we're going to do is when we have an identity, remember we're going to have a left side and we're going to have a right side. And what we're going to do is we're just going to pick a side. We're going to pick the side that's the most complicated, the easiest to simplify, to apply operations. You can see in all of these we had operation, well, not this one, but you could see like adding, multiplying, we had a lot of operations we can apply. So when usually one side is going to be much more complicated than the other side. Pick that side. If it's a toss-up, then just pick a side and you can always go back and try the other side. So we're going to apply operations. We're going to multiply, factor, add and subtract, as well as rationalize. Rationalize is multiplying by the conjugate. So you can see over here, this is an expression multiplied by its conjugate. And you can see what happens when you take an expression and you multiply it by its conjugate. Typically, we multiplied conjugates with complex numbers to eliminate the I, or we would multiply radicals by the conjugate to eliminate the radical. Well, for Pythagorean, for trigonometric functions or expressions, when we multiply by the conjugate, what that does is that creates a Pythagorean identity that we can then apply. So first thing, you're going to pick a side. Then you want to apply operations. Then the next thing is you're going to want to look for identities. So last class period, we talked about the reciprocal, the quotient, the even odd, the cofunction identity. Look to apply those identities. And again, our goal is to typically simplify that most complicated side, but really we want to make that one side look like the other side. So that's what we want to make sure we're doing. We're going to make one side look exactly like the other side. And then also kind of a little trick here is whenever you see something that's squared, look to apply the Pythagorean identities. I think I went over this with my students. Every single time that they saw a trigonometric function squared, we were applying the Pythagorean identities, right? So again, that's not always the case. Not every single time you see a trigonometric function squared are you going to be using an identity in one capacity or another. But it is very, very common when you have trigonometric functions squared that you will be applying the Pythagorean identities. One thing that when students get stuck, you're going to be working through these problems and you're not going to understand how to do something. You're going to try it maybe like 3 or 4 different ways. You're going to be really, really confused. piece of advice is just convert things to sines and cosines. You know, you can do that using the quotient and the reciprocal identities, as well as the, well, actually the Pythagorean. Yeah, you can also do it with the Pythagorean identities if you need, but convert everything to sines and cosines. So just get rid of tangents and secants and everything else. Just have everything in terms of sines and cosines. Sometimes that allows you to see what can be divided out or where you could go. Also, another tip is if you don't like the cosines and sines, or if that's kind of confusing as well, convert things to x's and y's. Sometimes for the algebraic operations, students do better with x's and y's than sines and cosines. But last class period, that's what I tried to help you guys out with, was working with these trigonometric functions. And again, try it one way, try it another way. I mean, just keep on trying. That is the main thing. I told students, you know, you cannot get frustrated on not understanding how to do the problem the first time you try it. Sometimes it's going to take 3 or 4 times. Sometimes it'll take you a half an hour or an hour a day, and you're not going to be able to figure out. Like, I remember when I was in high school showing up early to school to get help from my teacher because I would have problems that I could not figure out and they were just bugging me. And now I'd probably look at them, they'd be able to be so simple, you know, just from now, because I've solved so many of these. But again, it's just one of those things that it just takes a lot of practice. So take it slow, try. And then, you know, just try to keep on keeping your mind open to different things you can work on. And then last but not least is if you feel like you've really done everything you can do on one side, then just switch a side. But when we work on a side, we're only going to work on one side. We're not solving equations. We're not applying operations to both sides. We're going to pick a side and work on that side as far as we can go. All right. So let's go ahead and get on it. And that's all we're really going to do, guys, is I'm just going to kind of work through. That's all we did for this class. I didn't really teach much. Actually, I didn't teach at all. I just kind of went through those identities, and then voila, we worked through these examples. So obviously, I think you guys can agree that the left side is more complicated than the right side here. And so therefore, that's what I'm going to do. I'm just going to, first, there's not really any operations I can apply. Well, there is division, but there's nothing really I can apply right now. So the first thing I'm going to want to do is just go ahead and use my identities. So I recognize that cosine of pi halves minus theta is really sine of theta. And the cofunction identity, or sorry, the even odd identity for tangent squared is going to be a negative tangent of theta. Now again, I could rewrite this as sine of theta times a negative cotangent of theta, right? Instead of dividing by tangent, you could multiply by cotangent. And again, that's going to be cotangent is cosine over sine. And therefore, you can see that's going to equal a negative cosine of theta. So I'm not sure where I learned this or where I learned this or found this or was taught this. But a lot of times, since I'm only working on one side, I will just keep that equal sign kind of going down, do all my work on the one side. And then once I have the left side equal to the right side or the right side equal to the left side, I'll just kind of put a check mark there. And that's just kind of how I worked out. I think on this one, you guys could probably say that, fraction kind of looks a little bit more complicated than this one. Let's go ahead and do our first check here. We recognize a squared, so let's try to think of Pythagorean identities. I'm not going to keep on scrolling up. So if you see 1 minus sine squared, hopefully you recognize that is the cosine squared. Duh. Okay, so now I have, what happened? Oh, that's just sine. Okay, so now I have sine of x divided by cosine squared of x. And then really all I need to do is just kind of group this a little bit differently. So I can just put 1 cosine of x times here. And then I could just rewrite this as, cosine of x over there, right? Because cosine of x times cosine of x is cosine squared of x. And now I could just kind of group these, or another way that we look at this. This was always confusing. I can imagine this would be confusing to me. Like, why are you doing that? How are you allowed to do that? But a lot of times I just kind of grouped them for my students and said, yep, see how it works? Tangent of x times secant of x. So you don't really need to, I don't ask my students to show all this work, but I wanted to show this because I can imagine when I was a student, this would be confusing to me. But again, cosine squared is cosine of x times cosine of x. So therefore you can break those apart and just group the sine of x over cosine of x to be a tangent of x. And therefore now you can see the right side is now equal to the left side. All right, now this is one thing I want to be important. Like, I am not going to tell you what to do, right? In this case, I just said apply identities. Here, I'm not going to tell you to multiply, but I think it's kind of obvious. Yeah, you can multiply the right side, but again, this is much more complicated here on this left side. So let's go ahead and multiply. Now, unfortunately, this is not a difference of two squares here. I actually need to apply FOIL. So 1 times 1 is 1. 1 times negative cosine of x is negative cosine of x. Secant of x times 1 is going to be a positive secant of x. And secant of x times negative cosine of x is a negative 1. Now, it doesn't look like anything is really looks closer to multiplication here. I can see the 1 and the negative 1 are going to go to 0. So that's going to leave me with a negative cosine of x plus secant of x. All right, so here's kind of like our first test. I'm not really sure what I could do. I'm sure I can add these, but how do I add cosine of x and secant of x? They're not like terms, right? Well, again, let's do the convert everything to sines and cosines, maybe see if that allows us to like think of things in a little bit different light. So if I have negative cosine of x plus 1 over cosine of x, you can see that, oh, well, now I just got to get a common denominator, right? So to get a common denominator, I can see that is going to be a cosine of x. So I'll multiply by cosine of x on the left-hand side and a cosine of x on the right-hand side. Therefore, that's going to give me a negative cosine squared of x plus 1 all over my common denominator of cosine of x. Now again, going back to my identities, negative cosine of x plus 1 or 1 minus cosine squared of x. Hopefully you guys see that is going to be a sine squared of x all over a cosine of x. And then again, kind of doing what we did last time, we can just break up that sine squared of x. Sine of x times sine of x. I'm running out of space. All over cosine of x. And again, we want that tangent, right? So then we can just kind of group that. So therefore, that is equal to, all this kind of equal to a tangent of x times a sine of x. And there you go. So you can see how that kind of works in there. And obviously I'd want to have a little more space to show that. On this example, you can see the left side. So here's my point. Like the reason why we did those problems at the beginning, you can see how the left side is the obvious size to pick, right? Whereas this right side, there's really nothing else I can do. It's much easier to take this, simplify it to make it look like cosine squared rather than taking cosine squared and try to make it look like this, right? So let's go and multiply here. So by multiplying, I get sine of x times cosecant of x. Those are reciprocals, so that's 1, minus sine squared of x. Okay, well, this one's kind of basic. 1 minus sine squared of x using the Pythagorean identity is cosine squared of x. Wow, why was that one so easy? That one so hard, man. Jeez. I'm not sure, but I made it work. All right, now let's get into adding and subtracting fractions. And again, I'm not going to tell you how to do this. I just wanted students to see. I want to kind of give them a heads up on what to look for. So in this case, we obviously are going to want to add and subtract, right? You can see the left side in this first example is much more difficult than the right side. And again, typically, kind of like a rule of thumb, typically, is if you have an addition symbol on one side, addition or subtraction symbol on one side, and you don't have that addition symbol or addition or subtraction symbol on the other side, that means you're going to need to get rid of that addition or subtraction symbol by combining those terms or factoring out. It's not always the case, but a lot of times that's what we need to do. So in this case, I don't really see anything else easier I can really do. So let's go and combine them and see what happens, right? And again, it comes with practice. Some of you are saying, well, how do you know? Sometimes it works that way. Sometimes it doesn't. And again, it comes to practice. Try it. I mean, what's the worst that's going to happen right now? I'm going to get it wrong and have to try something else. That's it, right? Now, again, notice my denominator is going to be 1 minus a sine squared, right? So I recognize by obtaining common denominators, I am multiplying by the conjugate, which is creating a Pythagorean identity, which is important because that's going to condense that denominator. So in the numerator, I'm going to have a 1 minus sine of x plus a 1 plus a sine of x equals, I'll just simplify the denominator as a 1 minus sine squared of x. Okay. Now here, I notice that the negative sine of x and positive sine of x are going to add to 0, and I have 1 plus 1 is 2. So I have 2 over cosine squared of x. And now you can see, 2 over cosine squared of x using the reciprocal identity, that's going to equal secant squared of x. And there you go. Verified. For the next one is, again, kind of same thing. This is my point that I was talking about. Here's an additional symbol, here's not, right? So how do I add these, though? We kind of go back to that converting everything to sines and cosines. So here is going to be 1 over cosine of x, plus here is going to be 1 over sine squared of x. All right, so we don't have common denominators. So to get common denominators, I'm going to multiply by sine squared of x over sine squared of x. Over here, I'm going to multiply by a cosine squared of x times a cosine squared of x. Okay, by doing that, what I obtain now is a sine squared of x plus a cosine squared of x all over a common denominator of sine squared of x cosine squared of x. Well, obviously not obviously, not for everybody, but hopefully you recognize that sine squared of x plus cosine squared of x is equal to 1 over sine squared of x cosine squared of x. Okay, and then just using your reciprocal identities, you can see that's secant squared of x times cosecant squared of x, right? 1 over sine is, let's actually do this the right way. 1 over sine squared is cosecant squared of x, and 1 over cosine is secant squared of x. But it's important that you can still verify this, saying that is equal to that, because it doesn't, like the commuted product, it doesn't matter what the order that you're multiplying things. All right, the next one is rationalizing. So, one of that create is, multiplying by the conjugate. So if you can rationalize, what that's going to do is that's going to create a Pythagorean identity. Now, again, just to recap, we always, typically up to this point, we practice rationalizing for complex numbers. So therefore the I was not in the denominator, as well as multiplying by the conjugate or the radical to rationalize the denominator for the radical. So therefore we weren't dividing by an irrational number. Now, in this case, we're just trying to really, by rationalizing or multiplying by the conjugate, all this is really going to do to us is this is just going to, all this is going to do for us is just create a Pythagorean identity. So again, it doesn't need to be in the denominator. So a lot of students will pick this one because it's in the denominator. But again, you could do it. It's not wrong. But I just wanted to show you, you could also rationalize the right-hand side. And again, so all we're doing is we're multiplying by the conjugate of our Pythagorean identity. So whenever you see a trigonometric function, plus 1 or really just anything like, plus 1, a function plus another function or a number, you can look at that conjugate and multiply the conjugate. Just make sure you multiply on the top and bottom. So again, what's going to happen here is a secant squared of x minus 1 all over, I'll leave this out, a tangent squared of x times a secant squared of x, or secant of x minus 1. Okay. That's just a tangent of x. Okay, now using my Pythagorean identities, right? If you recall, it's going to be 1 plus tangent of x equals secant of x. So therefore, if I have secant squared of x minus 1, that's going to leave me with a tangent squared of x all over a tangent of x times a secant of x minus 1. So now, in this case, you can see that the tangent squared divided by tangent leaves me with what is exactly on my left-hand side, which is a tangent of x all over a secant of x minus 1. All right, so for the next one, I like this one because I remember actually doing a problem like this. I'm not sure if it was the same problem, but I remember this problem giving me so much fuss. So again, you can see there's actually 4 expressions that we could use as the conjugate. And I don't know how many, maybe I did all 4, I'm not really sure, but it doesn't really matter which one you pick. Just you want to multiply by the conjugate and just kind of go from there. So I'm going to multiply by this conjugate, sine of theta on the top and the bottom, just because I want to show you guys what this looks like. Okay, so when you multiply this, here you have to go ahead and use FOIL. So that's going to be 1 plus 2 sine of theta plus sine squared of theta. All over, here's the difference of 2 squares. So 1 over sine squared of theta. All right, it doesn't look like anything is getting any easier, right? And then I have 1 plus 2 sine of theta plus sine squared of theta. And let's see, that can be converted to cosine squared. And again, you're like, how am I still going to get to cosecants? Like now I just converted this to cosines. I don't have cosines on the right-hand side. So it's just not adding up. Like this is not working out the way that I want it to be. So again, just because you see something that you can multiply by the conjugate, and this is my point, like just don't always assume, try something. If it doesn't work out, right, then maybe try something else and say, all right, what is the relationship between sine and cosine, or cosecant, sorry. And you can see they're reciprocals of each other. And you can really see like these operations are really the exact same. It's just they are, this is one that's cosecant, that's sine, that's one. So what finally dawned on me, or I found the answer, I don't really remember, but it's, I remember just like not understanding what to do for this problem. But the answer is just multiply by sine of theta over the sine of theta. When you do that, what you obtain now, is sine of theta times cosecant is 1. Sine of theta plus 1 is sine of theta. All over, sine of theta times cosecant is going to be 1 minus sine of theta, right? So you could always just multiply as well by a trigonometric function or by a number to obtain the other result. So again, like sometimes just think about like how are they related? Maybe we can just multiply by a number to be able to achieve that result. And that's actually another technique that we're going to use again in these next two. So the next one is the distributing. So we just did adding and subtracting, right? You could easily add these two together. And guess what? When you do add these two together, it's going to make it look just like the other side. But my goal right now is just to kind of show you some different ways. So the one way is the distributing technique. So the distributing technique is basically saying, guys, remember A times B plus C is equal to A times B plus A times C, right? Good old distributive property. Well, again, remember that works for division as well. This is B over A plus C over A. So don't forget that. So if I have an expression divided by cosine of x, I can divide that as 1 over cosine of x plus sine of x over cosine of x. Well, 1 over cosine of x is equal to secant of x, and sine of x over cosine of x is equal to tangent of x. And it works. Now again, could you also rewrite this as 1 over cosine of x plus sine of x over cosine of x, which is equal to 1 plus sine of x over cosine of x? Absolutely, you could do it that way as well. Could you also just multiply? See, here I have a fraction, here I don't have a fraction. So what would happen if I just multiplied also everything by secant of x? If you multiplied everything by secant of x, you would get secant of x plus secant of x is cosine, so that's really going to be sine of x over cosine of x divided by 1, which is equal to secant of x plus tangent of x. So you can see how either one, there's like 3 different ways that we went ahead and kind of contribute for those. So I'm going to try to knock these down. I know my sun is kind of getting red on my shirt, so I apologize, but I want to get this video through here before the sun gets in my face, which is getting really close. All right. So there you go. There's 3 different ways, but the first way is the distributing way. So the next way, you can see that this looks pretty complicated on this right-hand side. But I recognize here this sine squared is cosine squared, right? So why don't we just go ahead and use my Pythagorean identities first. Rewrite that as a cosine squared of x. That is a cotangent, not a cosine. Now, again, I can use that distributing, and I can say, all right, cosine squared divides into cosine squared, so I can just rewrite this, distribute this. And cosine squared divided by cosine squared of x is going to be 1. Again, cotangent divided by cosine, you could rewrite that as multiplying by secant. Remember, cosine or cotangent is cosine over sine. So therefore, if you have cosine over sine times 1 over cosine, that's going to leave you with a cosecant squared of x. And 1 minus cosecant squared of x is equal to a cotangent squared of x. And therefore, it is verified. You could also do a couple of Pythagorean identities in that one. But again, just understanding that distributive. All right, the last technique that we're going to practice is the factoring. So we kind of did some factoring at the beginning. And again, like we also, could we have done... Yeah, we could have done, so we also could have done it different ways. And I think when I gave the students the problems at the beginning, nobody did factoring. They all wanted to like multiply it or do different operations. So my advice is, just remember when you see a function, again, in this case, doesn't really seem like one is more difficult than the other, right? So just pick a side. Pick what do you want to factor out, the sines or the cosines? Like it doesn't really matter. Let's just pick the right-hand side. But just notice whenever you have expressions separated and they have common terms, look to factor. So here I can factor out a cosine squared of x. By factoring out a cosine squared of x, I'm left with a factoring cosine squared of x, I'm going to be left with a 1 minus a cosine squared of x. Now, again, that gives me a cosine squared of x times a sine squared of x. Now, this is usually where students get stuck. They're like, all right, so now what do I do, right? I need to get these both to be sines. I have now a cosine times a sine. Well, now, again, we can use the Pythagorean identity to make that a sine, right? Cosine squared is 1 minus sine squared of x times sine squared of x. And now you can use multiplication to give you sine squared of x minus sine to the fourth x. And now you can see that's verified. So in this case, what we did is we used identities to simplify, but then we actually used identities to actually expand it back over. And one of these also might be to work on both sides that you could do also to verify. But I always like to keep it on one side. So sometimes you're going to be simplifying and then actually have to expand it back to get to it to equal the other side. All right, the last one, we're obviously going to pick the left-hand side. And you can see these trigonometric expressions both share secants. So what I'm going to do is I'm going to factor out a secant squared of alpha. And that's going to leave me with a tangent squared of alpha plus 1. All right, and then using my Pythagorean identities, tangent squared of alpha, I know is going to equal secant squared. So I have a secant squared of alpha times a secant squared of alpha is now going to be equal to a secant to the fourth of alpha. And there you go, ladies and gentlemen. That is how you verify the identity. So that's where we left off as far as what students understood. And, I could have done more examples. This really took us a whole class period to really work through this, and I didn't really do too much teaching. This was students really practicing working on these. And obviously, I just went through these very quickly because I've already done them, but also I've had a lot of practice with these. And so I recommend, if I was to give you all of these, they would take you probably, depending on your familiarity and skill set, but typically they're going to take you a lot longer to kind of work through because you don't know how to approach each and every problem. And again, my just advice, guys, is it takes time, it takes practice, but keep on working through them. And again, look at those operations, the factoring, the distributing, the rationalizing, the adding and subtracting, the multiplying, as well as just looking into converting identities. And if you get stuck, try to maybe do something else or use a different identities or pick another side. But it really just kind of comes into that practicing for that students struggle with, because it'd be much easier if I just said, do this every single time. And that's just not the way this, section works. You basically have to kind of get familiar with different types of identities and how they are related to each other, and therefore you can start picking up on those patterns to make it a little bit easier. So there you go, ladies and gentlemen. That is my lesson on verifying identities. I hope it was helpful for you, and I look forward to seeing you in the next video. Cheers.